We'll see the structure of atom from the 10th class textbook. We have studied in our early classes about the subatomic particles. Those are electrons, protons and the neutrons. Electrons are of negative charge, that means -1, that is negative. These are very small mass and moves around the nucleus. See, this is the positive nucleus. In this nucleus we have the protons and the neutrons, whereas the electrons will revolve around the positive nucleus in the orbitals. These are the electrons. This is the atom. Now protons are of positive charge. Charge is +1. These are located inside the nucleus. In this we need to know that number of protons is equals to atomic number. If atomic number is 1, that is hydrogen. So number of protons is equals to atomic number. Next is the neutrons. Charge is 0. It is neutral. Also inside the nucleus. Neutrons are also inside the nucleus. It helps in mass and stability of the atom. I explained this how the neutron helps in mass and stabilizing the atom in the shorts video. You just check it out. Next question is, in this they asked that how do these subatomic particles coexist in an electrically neutral atom? This means how can this positive and the negative charges exist together? We know that number of protons is equals to atomic number. Number of protons is equals to number of electrons. So charge cancels out. So if the example, if we take protons is equals to +1, electrons are -1, then the total charge will be 0. I'll explain this in easy way. Suppose if we take a particular element, the number of protons stays fixed. The protons will always be fixed. Protons are, we know that it's of positive charge. So for an atom to become neutral, suppose if we want an atom to be neutral, it needs some same amount of electrons, right? Because electrons are negative charges. If we take the example that is of carbon, that is neutral, means it has 6 protons. Carbon means atomic number is 6, so number of protons will be 6. Charge of the carbon protons is +6 charge. So electrons are also will be 6 electrons, then -6. See, protons will always be fixed. In carbon protons are 6 protons. In order to make it neutral, it needs same number of electrons. See, now 6 electrons comes to adjust the neutral position of the carbon. So 6 electrons means -6 charge. These both cancel and the atom becomes neutral. Suppose the atom loses its electrons, then it becomes positive ions, that means cation. If it gains electrons, then the atom becomes negative ion, that is anion. But the number of protons usually does not change in normal chemical reactions. The number of protons will be constant. Okay. You see the example here. Someone gave you 10 rupees and they took the 10 rupees. Then what will be the amount of you will have? 0 only, no? In the same way, if the proton has +1 and the electrons are -1, then the total will be 0. Then the atom will be neutral. We already know some basic atomic models. I have already discussed in earlier videos. Now we'll see them in short. First one is J.J. Thomson model. He said that atom is a positive ball with electrons present inside it. Where this is also called as plum pudding, means raisins inside the cake, and it's also called as watermelon model. This red portion is completely, that is positively charged. Completely it is of positively charged, whereas the seeds are represented as the electrons. This is called as J.J. Thomson model. He could not explain where this positive charge is exactly concentrated. Okay, electrons are inside a positive charged ball. Next, coming to the Rutherford model. Atom has nucleus at center, mostly empty space. Electrons revolves around the nucleus. He said that atom is consists of a positively charged nucleus, and he could not explain why the electrons are not falling into the nucleus. Okay, why the electrons are not falling into the nucleus when they revolve around the positive charged nucleus. Next one is Niels Bohr's model. He said the electrons moves in the fixed circular paths. These are called as cells, and energy levels are fixed. And we learn these all things in detail in this chapter. Now, students should make the model that is of atom. We took the thermocol balls as the nucleus, and small beads are electrons, wires are orbits. The purpose of this activity is it helps to visualize the atomic structure exactly how it looks. We'll see the activity 1. Can you arrange the subatomic particles in any other way in an atom? Can you arrange the subatomic particles in any other way in an atom? Students can try different arrangements, but we can't keep the exact real atomic models. We can arrange them, but it will not be exactly the scientific way.
And do all atoms have the same subatomic particles?
Yes, we'll have the electrons, protons and neutrons, but the number differs. Means atomic number is equals to number of protons. Here atomic number of hydrogen is 1, so number of protons will be 1. Oxygen 8, so number of protons will be 8. We can have all the same, but the protons only will differ here.
Why is an atom of one element different from the atom of other elements?
Only because of the protons, no, right? Atoms of other elements, see, main reason is number of protons, atomic number. Each element have the unique atomic number. Hydrogen means 1 proton, carbon means 6 protons, oxygen means 8 protons. It only varies in the atomic number, that is number of protons. The identity of a particular element depends on the number of protons.
And how are the electrons distributed in an atom?
This means where do electrons exactly stay? K shell means 2 electrons, L shell 8 electrons, M shell 18 electrons and N shell 32 electrons. We know that the positively charged nucleus consists of the shells, subshells and this is N is equals to 1, N is equals to 2, N is equals to 3, N is equals to 4. In this one we have one subshell. This have 2 subshells. I have already discussed in the earlier video. You just look into that. So it has 2 subshells. In first cell, this is a K shell. This is L, M, and N. K shell has only S orbital. That is 2 electrons. We have 2 electrons. It has S and P orbitals. S orbital has 2 electrons. This has 6 electrons are present here. For this, we have a formula that is 2n square. If n is equals to 1, that is formula is 2 into 1 square, that is 2 electrons. See, in the first cell we have only 2 electrons. If n is equals to 2, 2 into 2 square, that is 2 into 4, that is 8 electrons. In the second cell we have 8 electrons. In this first one, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons. In this way, M shell has 18 electrons and N shell will have 32 electrons. This was the formula. To understand electron behavior, we study light and spectra. Okay. And this gives the color. That is, sodium gives the yellow flame, copper gives the green flame. Why the electrons gives the color? Because here the electron jumps from ground state to excited state and the excited state to ground state. When the electron jumps, energy changes and the light emissions will occur. A real life example is, have you seen a rainbow after rain? Rainbow forms when sunlight passes through the water droplet. Okay, here there is a prism. When we pass the light, this gives a different spectral lines. In the same way, the water droplet also acts as a prism and the light split into different colors.
How many colors are there in a rainbow?
We know that there are 7 colors. Here the mnemonic is, we know that we'll call it as VIBGYOR. V represents the violet, I, indigo, blue, green, yellow, orange and red. Okay, you know that it is a continuous spectrum. Means the colors were not separate. They merge into each other smoothly. Okay, colors are not separate blocks. They merge smoothly into each other. The intensity of each color varies from one point to the other. In some colors looks brighter and some are faint. We see some colors are bright in the rainbow and some colors are faded. Okay. Next, coming to the wave nature of the light. When you throw a stone into the still pond, when we throw a stone, then we see the ripples like this, isn't it? We see the circular waves formed. These waves carry energy, not water itself. These are not carrying the water outside. These are just carrying the wave energy here. Wave here transfers only the disturbance in the form of waves on the surface of water in all directions. You see, the water is not flowing outside, no, only the waves are just moving. Only the disturbance is happening on the waves. We know that when something like a drum vibrates, then the sound waves are produced. Vibration happens, then the waves are produced and we hear the sound. Same concept applied to the light here. Electromagnetic waves are produced when an electrical charge vibrates. This means moves back and forth. In order to understand this, you should know about this particular concept. Suppose when people say charges moves or vibrate, that means the charged particle themselves are moving a little. For example, in a metal, positive ions stays mostly fixed in a particular. We know that our positive charge is fixed to a particular place. Mostly it does not move. Electrons only move around the orbitals, around the positive nucleus in the orbitals. Okay, electrons can move around. When electricity flows, mainly the electrons move through the material. In current, electrons does not travel all the way from one city to another. Means, suppose if we take the wire, the electrons are not moving like this. Just the electrons are present in this particular area. They just move front and back. They just vibrate. They move back and forth, just vibrate or oscillate in their place. Vibration means the charged particles shake or move slightly. Okay, they does not go all over the wire or like that. This is the electrical charge. Electron, we know that is of negative charge. Protons are of positive charge. Here, their movement creates the electrical effect. Suppose if we take a stationary charge, that is of positive charge or a negative charge. If we take a stationary charge, it only creates the electrical field. If a moving charge, if it is moving, then it creates the electrical field and the magnetic field. A moving charge creates both the electrical field and the magnetic field. The magnetic field forms in the circles around the moving charges or current. This magnetic field forms in circles. Suppose for a straight line carrying current, that is perpendicular idea comes from the direction relationship. That is, we will take the current direction. If the current direction is in this way, then the magnetic field direction will be in this way, in the circular way. We know that the magnetic field forms in the circles. If the current is in this direction, then the magnetic field will be in the circular direction around it will be perpendicular. If current is upwards, then it will be perpendicular to it. These directions are the right angles to each other using the right hand thumb rule. Suppose if we take this, if the current is in this direction, then the electrical field will be in this direction. Okay, the electrical field will be moving in this direction. This is upward, this is perpendicular to it in this way. This is the right hand thumb rule. Okay, did you understand? This thumb is in the this is upward thumb, this is the current. Then the fingers will be in this way. This is the curved fingers are the magnetic field direction around the wire. Here, moving charges creates the magnetic field. This magnetic field direction is perpendicular around the current path. Now coming to we know that is charging electrical field. This creates the magnetic field. This magnetic field creates an electrical field, vice versa. When this both fields travels each other and travel through a space, it creates a wave. Suppose if electric field oscillates, magnetic field also oscillates. Both are perpendicular to each other, then the wave moves forward. Suppose we'll take the light wave or radio wave or the X-ray wave. In this, it consists of both the electrical field and the magnetic field. These two produces the wave. That wave move forward. These waves all are called as electromagnetic waves. This light wave is also called as electromagnetic wave. The radio wave is also called as magnetic wave. All called as electromagnetic waves. Now you can understand this concept. A vibrating electrical charge creates the charge in the electrical field. This changes creates the change in the magnetic field. Charge vibrates, electric field changes. Electric field changes, magnetic field forms. So both fields are connected. These both fields are connected and produces the wave. We know that. We have already discussed now. This process continues with both the fields, that is magnetic and electrical field, which are perpendicular to each other and right angles to the direction of the propagation of the wave. If the electrical field is up and down, then the magnetic field will be in this direction, and the direction of will be in the forward direction. All are mutually perpendicular, that is 90 degrees. See, in this textbook we can see that the direction of wave is in this way. The electrical field is in upward direction. This is the magnetic field direction is in this way. All three are in the perpendicular to each other. They are 90 degrees to each other.
This is the electrical field, this is the magnetic field, which are perpendicular to each other, and the propagation of the wave is in forward direction. These all are perpendicular to each other.
Now, visible light is also called as electromagnetic wave. We know that electromagnetic wave can be light or radio waves. Any wave can be the electromagnetic wave. Here, suppose we took the visible light is the electromagnetic wave. The speed it is speed with how much speed the visible light it travels is 3 into 10 to the power of 8 meters per second. Light travels very fast. Light travels with how much speed? 3 lakh kilometers per 1 second. It travels 3 lakhs kilometers. What are the characteristics of EM, electromagnetic wave? The wave can be up and down pattern. We know that it moves up and down. Wavelength is the distance between two peaks. Suppose this is the wave. Okay, this is the wave. The up and down motion is the wave. The wavelength is the distance between the, this is the distance. The distance between the here this was the distance between the two peaks. This peak is called as crest. This down peak is called as trough. Okay, wavelength is the distance between the two peaks. Electrical field means one wave direction. Magnetic field is that is perpendicular to the electrical field. This suppose if we take this is the electrical field, then the magnetic field directions will be somewhere like this. We saw that it will be in this way, some which is very perpendicular to the electrical field. The direction of the wave will be in the forward direction. Now I have shown you from the textbook in that way. The electric magnetic energy travels through a vacuum, behaves in the same way like ocean waves traveling through the water. We know that our ocean waves also needs water. It carry the energy. Means just the waves movement, it needs water. But the light waves does not need any medium is not required here. Light can travel through the vacuum, means only space. It also carries the energy. Like ocean waves, electromagnetic energy is also characterized by the wavelength and the frequency. What do you mean by this characterized means? That is recognition or the identification. Suppose if you take the tiger, it is characterized by the black strips. The tiger will have the black strips, no? Means that is the characterization. In the same way, the electromagnetic energy is also characterized by the wavelength and the frequency. Okay, two important properties are the wavelength and the frequency. Wavelength means the distance between the two waves. Frequency is number of waves per second. Wavelength is the size of the wave. Means this is the wave. The distance between these are the crusts. These are the troughs. Okay, these are the crusts. These are the troughs. The distance between the two crusts or the distance between the two troughs is the wavelength. That is the size of the wave. A wave has repeated peaks and the valleys. These are the peaks and these are the valleys. The distance between two consequent crusts or troughs is called as wavelength. This is the wavelength. Think of the ocean wave. The distance between the two waves is called as wavelength. Frequency tells us how many waves that pass in 1 second. Suppose if 5 waves pass in 1 second, the frequency will be 5 Hz. The frequency is expressed in units of reciprocal seconds. Seconds is this one. Reciprocal second means 1 by s. This is represented as s minus 1. This is called as Hz. Okay. Frequency unit is Hz. 1 Hz is the wave per second.
Now we'll see the relation between these quantities, that is lambda, mu and speed of the light, that is c.
I'll explain the relation between these quantities that are lambda, mu and speed of the light. For electromagnetic waves, c is equals to nu lambda. C is the speed of the light, nu is the frequency, lambda is the wavelength. Since c is constant for the light in vacuum, then lambda is equals to, you keep this lambda this side and this nu comes down. Lambda is equals to c by nu. Here for the light in vacuum, c is constant. So we'll take this. Lambda is inversely proportional to 1 by nu. See, when we remove this constant, we'll use the proportionality symbol here. So now frequency increases, wavelength decreases. Okay. If it is high frequency, then it will have the small wavelength. Suppose if we take the radio waves, it has the low frequency, then it will have the high wavelength because they are inversely proportional to each other. Here, as they are inversely proportional, frequency increases, wavelength decreases, wavelength increases, frequency decreases. This formula works for all waves, light waves, sound waves and water waves, whatever might be, electromagnetic waves. High frequency means small wavelength, low frequency means larger wavelength. Gamma rays will have the high frequency, so small wavelength. Radio waves will have the low frequency, then larger wavelength. And all types of electromagnetic waves are arranged by frequency or wavelengths, known as electromagnetic spectrum.
See, this is the electromagnetic spectrum from cosmic rays, gamma rays, X-rays, UV, IR, microwaves, radar, radio waves and broadcast band. In this here, this is the visible range. This line is the visible region. Left of visible light we have the UV rays and the right of visible light we have the infrared rays. Only this is the color region where we can see. This complete region is invisible.
Electromagnetic waves can have a wide variety of frequencies. Light is not just one type, it includes many types with different frequencies. Suppose, see this, from gamma rays to we'll have radio waves. Gamma rays will have the shorter wavelength and high frequency, whereas radio waves will have the less frequency and high wavelength. First we'll have the gamma rays, next X-rays, UV rays, visible, IR, micro and radio waves. The wavelength increases from the left to right. Frequency increases from right to left. This is the visible region. This is the range of light our eyes can see. It will be from violet, blue, green, yellow, orange to red. The range is from 400 nanometer to 700 nanometer. Only this we can see with our eyes. Left side of visible region will have the UV rays. That means shorter wavelength which are invisible. Right side of visible region will have the IR rays that are longer wavelength and these are invisible. These all are invisible. Only this visible region we can see with our eyes. They are from the 400 nanometer to 700 nanometers, which includes the colors like violet, blue, green, yellow, orange and red.
What happens when you heat an iron rod on a flame? And do you find any change in color on heating an iron rod? We'll discuss this now.
What happens when you heat an iron rod on a flame? It starts glowing. First it becomes red, then yellow, then white. It will be very hot. Do you find any change in color? Yes, on heating an iron rod, the color changes due to the increase in temperature and frequency. When we heat iron, it does not just become hot. It starts giving out light energy. Heat energy is converted to light energy. At low temperatures, iron glows red. Low means not cool like ice or room temperature. That is just lower compared to the very high temperatures needed for the white glow. Okay. Suppose if you take the red light, it has the low energy and the long wavelength. If we take the iron at room temperature, we cannot see any glow here. If we heat it more, we'll get the dull red color. If we heat it much more, then we'll get the bright red. If we heat it continuously with more heat, then at final it becomes the white color. Okay. We have two important relations here. C is equals to nu lambda. We know that if frequency increases, wavelength decreases. Next one is the Planck's-Einstein equation. In this, we can conclude that if frequency increases, energy also gets increases. So that when we connect all these things, we can know that if temperature increases, energy increases. If energy increases, frequency also increases. Frequency increases, wavelength decreases. If low temperature means low energy means low frequency means high wavelength. Okay, these all are directly proportional. This only wavelength is inversely proportional. At lower temperatures, color is red, energy is low, frequency is low, wavelength will be high.
Do you observe any other colors at the same time when one color is emitted?
Yes, other colors are also emitted, but they are not clearly visible because one color has high intensity. When an object like iron rod is heated, it actually emits many wavelengths, many colors at the same time. But one color becomes stronger, which is dominant. So our eyes mainly see that one color only. At lower temperature, we can see the red color, which is very strong. At other colors are also present, but very weak, which are not visible to our eyes. At higher temperature means more colors appear, finally looks. At higher temperature, it becomes very hot and finally it looks white. This is the mixture of all colors. Earlier belief was energy is continuous that is any values are possible, but Planck said that energy is not continuous, energy is released in the packets form, that is quantized. Energy is equals to n into h mu. Here n is the number of units. If energy comes in steps, h mu is 1 unit, 2 h nu is 2 units, 3 h nu is 3 units. It cannot have 1.5 h nu, 2.5 h nu. Only the fixed amounts are released here. Energy of certain frequencies is represented by the equation, that is E is equals to h nu. E is the energy, h is the Planck's constant, nu is the frequency. H is the constant, very small constant value, that is 6.626 into 10 to the power of minus 34 joules per second. Nu is the frequency of the radiation observed or emitted. That is frequency determines energy. Higher frequency means higher energy. Red light has low frequency, low energy. Blue light have high frequency and high energy.
Next one is, do you enjoy Diwali fireworks? Variety of colors is seen from fireworks. Yes. Fireworks in Diwali produce different colors due to the different elements. Fireworks contain different chemicals. They are metal salts like sodium, copper, strontium. When they are heated, the heat energy is given to the atoms. Suppose this is the atom. When the heat energy is given to this atom, this has the nucleus and the electrons are present in this shells. So the electrons gets excited and again they come to the ground state. When they come to the ground state, they release the energy. Okay, see, electrons gets excited, then they are heated, heat energy is given to the atoms, and the electrons gets excited from the lower energy level to the higher energy level, and the electrons come back to the original level by releasing energy in the form of light. Each element have different energy levels, so different elements exhibit different colors. Sodium gives the yellow color, copper gives the green or blue color, strontium gives the red color. Energy of the light depends on the frequency. We know that E is equals to h nu. Different energy means different frequency, we get the different colors. Each element emits a characteristic color because electrons release specific energy when returning to the lower energy levels. Coming to the lower energy levels means this is from ground state to excited state, from excited state to ground state. This is the ground state. When they come to the lower energy, they releases the light energy. Now we'll see the activity 2. Take a pinch of copper chloride in a watch glass and make a paste with the concentrated hydrochloric acid. Take this paste on a platinum loop and introduce into a non-luminous flame. What we have done here? Now we take a pinch of copper chloride, that is CuCl2. It contains copper ions Cu2+. These ions are responsible for the color. Now make a paste with the concentrated HCl. You take this copper chloride and make the paste with add this concentrated HCl. Here HCl is used for the converting the salt into a volatile form. Volatile means evaporating. Helps the substance to vaporize easily in flame. This HCl helps the sample burn properly and shows the clear color. Now we'll introduce into a non-luminous flame. Non-luminous flame means it does not mean no color at all. A blue flame is called as non-luminous because it is not bright yellow or glowing. The combustion will be almost complete. So gas stove blue flame is the non-luminous flame. Candle yellow flame is the luminous flame. It gives the glowing soot particles. Why not yellow flame means it already has color due to the soot. It will disturb observation. Blue flame means it is clean, colorless and best for the flame test. Now what color will observe? That is the green color. This is the characteristic of copper. Copper means it gives the green color or blue color. Repeat the same with the strontium chloride, SrCl2. We'll observe the crimson red flame. This is the characteristic of the strontium. What is actually happening here is heating gives energy to atoms. When we heat the atoms, electrons gets excited from the lower energy levels to higher energy level. Electrons return back, they cannot stay excited for the long time there, so they return back to the lower energy state. Now when they come to lower energy state, the energy is released as light of specific colors. Because each element has different energy levels and different energy gaps, so emitted light is of different colors. Sodium is yellow color, we see in the street lamps. Copper is green or blue color. Strontium gives the red color. Potassium gives lilac, means light purple or lavender color. Calcium gives the brick red color. Here, what color did you observe? That is the green color. And the similar activity is done with strontium chloride, we get the crimson red flame. Do you observe yellow light in the street lamps? Yes, due to the sodium vapor lamps. Sodium gives a bright yellow color. Why do sodium vapors produce a characteristic yellow light in street lamps? This leads to an important question. Why do different elements emit different colors even when heated in the same non-luminous flame? Scientists found that each element emits in its own characteristic color because the electrons in the different atoms have unique energy levels. When these electrons are heated, their electrons gets excited to the higher energy states, and upon returning to the lower energy states, they emit energy in the form of light. The emitted light has specific wavelength which are not continuous but discrete. Discrete wavelength means only specific values. A quantity can take only a certain fixed values. It cannot take values in between. Not all values means 1.1, 1.2, 1.25 like that. It takes only 1, 2, 3, 4. Okay. It only takes these fixed values, discrete values. Not continuous. Continuous means it takes all values, means 1.1, 1.2, it takes all values. Discrete values means only 1, 2, 3, only specific values are taken, which are not continuous but discrete, meaning only certain fixed wavelengths are produced. These discrete values appear at a distinct bright lines in a spectrum and therefore called as line spectra. Since each element has its own unique set of spectral lines, these spectra acts as the fingerprints and can be used to identify unknown elements. Just as the fingerprints are used to identify the individuals, these are the line spectras. In these fixed discrete wavelengths are appeared as the distinct bright lines in a spectra. Therefore, these are called as line spectra.
If you like the video, please do like, share and subscribe.